did research and collaboration in number theory for this sabbatical. And the intent was to work mostly with the group at the University of Oregon that was quite possible to do a lot of collaboration through Zoom and through email. I also participated in seminars at the University of Oregon and other institutions. The third part of the sabbatical, I had intended to accompany the researchers to the Arizona Winter School in Tucson the first week of March. The winter school was canceled, and so it was replaced with the Arizona Virtual School. And so I was able to participate in that as well. I wasn't officially placed in one of the discussion groups because of demand by young students, but I was able to find some people who were interested in this and organized an informal discussion group so we could discuss the lecture material and problem sets. So I'd like to give you a little bit of a flavor of the sort of problems that we looked at. There's much more if you want to look at the sabbatical report. Has a lot more of the mathematical details, but just give you a little bit of an idea. There's an old problem. Given any positive whole number, how can you write it as the sum of two squares? And some numbers, there may be one solution. There might be more than one solution. Some numbers, there are actually no solutions. So in general, it turns out that the problem of finding all the solutions is closely related to the problem of factoring n into its prime factors. Now, in number theory, which is related to algebra, often we like to use graphs and try to get a geometric intuition about what's going on. So, for example, if I look at all the solutions to x squared plus y squared equals 65, we get a nice circle for the graph. There's an infinite number of points on this circle, so there are an infinite number of solutions. But if we're interested in only the whole number solutions, those show up as the green dots. So for example, 8 squared plus 1 squared or 7 squared plus 4 squared. And by allowing x and y to be negative numbers, the generality is actually useful. So we see we actually have, if you count positive and negative numbers, we have 16 solutions here. We might want to generalize this. Maybe we want to find not just whole number solutions, but fractional solutions. And it turns out that we can characterize quite easily all of the fractional solutions. I give an example here for x squared plus y squared equals 10. The set of all rational numbers is what we call a field, because you can always add, subtract, multiply, or divide any two fractions and get another fraction. Of course, you can't divide by 0. That's the only exception. But a number field is what you get if you start out with the rational numbers, the fractions, and you throw in one or more irrational numbers. So I have an example here, square root of 2. If you also include numbers that you get from fractions and the square root of 2 and the 4 basic operation, you find other solutions. And so, number theorists would also like to characterize how many solutions, what are the solutions to this equation in this number field. Now, the interesting thing about number fields, of course, again, we have to consider prime factorization. But sometimes in a number field, a prime number is no longer prime. In the extended field, you can still factor any number into prime numbers, but an interesting fact about number fields is that prime number factorization is not always unique. Another problem, which was studied in the Arizona Winter School or the Arizona Virtual School courses, was this 4 squares problem. Given any number, how many ways can you write it as the sum of 4 squares? And Jacobi proved in the 19th century that solutions there's always at least one solution to this problem for any positive value of n, he found an interesting connection to the theory of modular forms. And modular forms have become a very important topic in number theory research now. So one of the courses at the Arizona Virtual School centered on this connection. And that's a central interest of the research group that I worked at the University of Oregon, modular forms and also their generalization, automorphic forms. So thanks for this opportunity. I found working with a group like this where I was more the student than the teacher was very illuminating. Felt like I got some interesting lessons I can apply in my own teaching. I would encourage you to maybe look at the sections of my sabbatical report that talk about this. If you want the mathematical details, they're in the third section, and you can gloss over that if you're not interested. But I think some of the other observations you might find interesting. So thank you very much. And this has been quite a fun experience for me.